Okay, we're getting recorded. Great. Welcome to our workshop on traffic infrastructure mapping and automated damage assessment systems, which takes place as part of this year's ICDS conference. I'm glad that the conference is hosting our workshop in this course. Also because we, as a project of Esrium, but also as a community concerned with traffic infrastructure digitization, see a growing demand on sensing systems, and sensing systems in a mobile world typically are contactless, which means computer vision systems, LiDAR systems, radar systems are generally applied and in place, and therefore you ultimately get out vision system problems. So you need to solve everything concerned with data acquisition, data analysis, data provision, but also in terms of the various aspects of resolution, time synchronization, geolocalization, and so on. So in the end, we are talking about complex overall systems which need also be addressed at this level. And therefore, this is also the motivation for today's workshop. I hope we put together many very interesting talks on these topics, which cover, so to say, the whole value chain of data sensing up to data provision and data usage. And we will also present various use cases on these types of data. A few short introductory words to the workshop itself, some administrative words. My name is Matthias Röther from Ioneum Research. I'm coordinating this workshop. My co-moderator today is Martina Uray, who will also take care of some administrative things there, putting up polls and so on. Regarding the sequence of presentations or the organization of the workshop, we will have an agenda filled with talks. We will have, like at 10:30, a short break in there. And in parallel to the talks themselves, of course, you're always allowed to ask questions. Please use the chat for that. After each individual talk, we will have a look at the chat, and then there is always a 5 minutes Q&A session where we will discuss the individual questions. In parallel to the talks, we will also set up some polls, so to get your opinion on the presented content and get your suggestions. On the slide, which is shared by now, you can see the link to this poll. It's also encoded in the QR code, or you can go to, say, slido.com and fill in the meeting ID here. So with that, you will be able to participate in the polls, and we'll also present the results. Regarding presentations, as an audience, please do not share video in order to save bandwidth. The speakers, of course, are encouraged to share their video feed during presentation. So having this said, I will give you now a short introduction on today's workshop. Regarding the agenda, we will start with two very interesting keynote speeches. We will get use cases and demands from two fields of mobility. One is rail infrastructure and one is road infrastructure. Then we will have like a 10 minutes break. And then we will go into the various aspects ranging from use cases which can be built upon digital traffic infrastructure. We'll touch the field of sensor technology, which is there and can help digitize our traffic infrastructure. Then, of course, data platforms are a topic. Communications on the road infrastructure, so feedback to the users of this traffic infrastructure. And driving functions, building automated driving functions, building on top of digital content. And then afterwards, we will do a closing remark. We will collect again your feedback, and we will hopefully also have much interaction from your side and suggestions on what the future will bring us in this field. So in general, what is the motivation now for digitizing traffic infrastructure? The major goal in all of those fields is like to create digital twins, which will play an increasing roles in like increasing our level of automation. This is important on the road, but also an increasing topic on the rail. So automated mobility, more on-demand mobility, and also making this mobility more resource efficient. This also brings us to the second field where we want to use those digital twins to optimize certain processes regarding traffic infrastructure, which includes, of course, the traffic management on it. So optimizing its usage on one hand, but also, and probably in the short term, even more important, optimizing maintenance, which means simulating and predicting the use and the life cycles of individual components in this traffic infrastructure, and then doing highly optimized maintenance operations. And the ultimate goals out of that is to provide greener, safer, and smarter mobility solutions. So reduce resource efficiency in maintenance, but also in usage, make our mobility safer in the end, and also smarter by creating additional and probably new and disruptive services using this infrastructure. So the goal of this specific workshop here now is to bring together stakeholders from all the various fields concerning the creation of digital traffic infrastructure twins, which come from traffic management and operation on one side, then from sensing and data acquisition on the other side, data analysis and information extraction, and finally, data management and data provision and distribution to the end customers. This whole workshop is supported by the EU H 2020 project Esrium, where we address a very specific field of this very general topic of digital infrastructure twins, which deals with the digitization and assessment of road wear damage. So here, the digitization of damages is the major topic. Here you can see the participants within this project. We have a highly international list of cooperating partners here from Austria, Finland, Italy, Spain, Hungary. And you will find more information on the individual aspects of this project later on during the individual talks. Now I'll just give a short overview on it. So the key innovation of Esrium is to create a digital map only of the road surface, and to create a map overlaying it with road damage and road wear. So in addition to like what you know from HD maps and from navigation maps on the road, we want to complement this information with a map of road surface damages, where they are, what type they are, and how severe they are. And then we want to automatically create this information, and we want to distribute this information. And in distributing this information, we will follow two use cases there. So we want to distribute this information on the one hand to automated vehicles. We want to feed them back so that they can use their information to make their mobility safer in the end. But they can also like distribute their road wear more easily or more better along the lanes, so that, for example, you can reduce the overall wear of the lanes and then increase the lifetime of the road surface. On the other hand, we will feed it back to the road traffic infrastructure maintenance, where maintenance in this course can be planned in more detail and thereby also be optimized in terms of usage of resources for maintenance. So looking a bit on the time, we will get back to the use cases later on in the more detailed presentations. So now I will quickly jump over it. I guess you will see all of these images later on. I want to thank you all for taking the time and participating in our workshop. I will hope for some interesting discussions on the individual topic. And having this said, I will now give the stage to Michaela Haberler-Weber from ÖBB Infrastructure to give us an insight on the individual challenges, especially on the rail infrastructure.
Yeah, good morning. Can you hear me properly?
Yes, thank you.
Okay, so I will try to share my screen. So I hope you can see the slides.
Not yet, it's still loading with me.
Okay.
But it said you started screen sharing.
So it worked an hour ago, so.
Yeah.
Perhaps I stop it and I start it again. So, also noch once again.
Yeah, now I see, I don't see the full presentation, but the PowerPoint.
So now you can see. Okay, perfect. So sorry for the delay. So good morning to all of you. My name is Michaela Haberler-Weber. I'm working at ÖBB Infrastructure at the Research and Development Department. And I'm responsible there for R&D activities, like, for example, the digitization of our infrastructure towards a digital twin, which is the topic for today. I've learned that you work together on a big project on road asset management and digitization. And well, I would like to show you some impressions of another infrastructure of railway asset management and the digitization of it. And well, I'm sure that there are some different topics, but also that there are many similarities in the challenges and issues for that. So perhaps you know that 2021 is the European Year of Railway, and this is linked to the efforts of the to meet the Green Deal objectives. because railway plays, of course, a significant role to reach all these ambitious climate targets. It seems to be clear that to reach these targets of the Green Deal, parts of the mobility of today has to be shifted towards railway within the future. And well, ÖBB, as we are the Austrian Federal Railways, we are Austria's largest mobility provider, and we are covering passenger transport, freight transport, and infrastructure management. And we at ÖBB Infrastructure Company, as the infrastructure manager, we are planning, building, and operating the Austrian railway network. So our focus is to provide this network to our customers, which are the various railway undertakings with highest availability. And on the next slide, you can see some basic issues of infrastructure managers. I've mentioned availability. So of course, we always have to increase availability, the availability of our network for our customers. But on the other hand, we have to be very cost efficient. So we have always to reduce investment costs and maintenance costs, for example. And now, additionally, with this mentioned shift of mobility towards railway in the future, we expect that we have to provide more trains, so more capacity to our customers. And the challenge now is to make the existing infrastructure more performant, more resilient, and more available, while at the same time reducing life cycle cost. And we see that here the digitization of our infrastructure is one enabler for that. And of course, within this very complex railway infrastructure system, there are several dimensions. For example, train operation, asset management, and energy demand, among others. But for today, I will focus on some parts of asset management, of course. So here you can see some basic questions of infrastructure managers. So for example, what is the behavior of our assets when we increase train operation by, for example, 30% on a certain line? What about the condition and the wear of tracks, of switches, and other structures? How to choose the best procedures and measures for a certain line? And what about new components, new materials? What about the innovation cycles? Just imagine that our tracks and sleepers, for example, they have a lifetime of about 20 to 30 years. And structures like bridges and tunnels have even longer lifetimes. So a tunnel that is built at the moment, like, for example, Semmering Basis Tunnel, will have a lifetime of 150 years. So that's quite a long time for making innovations. So what we need is a system that can answer all those questions within short calculation time, let's say. So our vision is to build up a virtual representation of our infrastructure network and of all our assets, so that we can answer the questions regarding the planning of future network, regarding quality, availability, and to make the innovation cycles shorter. So this is our vision of our digital twin. And well, I suppose every one of you has a different picture in mind when talking about the digital twin. And for us, this twin regarding asset management issues should be a modular platform containing all the asset data, containing train operation data, data of other processes like maintenance and so on, so that we can simulate here certain situations and answer questions out of that. So what have we done up to now? What are we doing within the next time? I will give you now some very short impressions of past work, of recent work. And well, at first I would like to start with some basics, which we've done, well, let's say many years ago, because what we need is a basic reference system for all the upcoming things. So we created geometrically correct track network, which you can see on the left side here. You can see the tracks in blue and the switches in red, and this is a part of a shunting yard in Vienna. And this track network has a defined coordinate system. It has metadata and all the other things that you need so that you can put the other upcoming data layers onto it. So this track network will serve as a reference from now on. Then we have worked for a very long time on 3D measurement techniques. So we've tested laser scanning, airborne laser scanning, railborne laser scanning, and so on. Meanwhile, mobile mapping systems are state of the art, and I'm sure that I do not have to tell you some basics on properties and advantages of mobile mapping systems. So, but when we need here, when we have all this 3D data, what can we do with that? And well, one of the things that we were doing is a kind of automated object detection of signals. So we tried to use the 3D data to create an algorithm based on artificial intelligence to detect the positions of the signals. So the aim is to complete the asset documentation and to get coordinates for all our assets. Another example for this is coming from an ongoing project called TARO. TARO means towards automated railway operation, and here the digital twin of the infrastructure is one work package out of that. The object of interest here at the moment is, for example, the mast, which is standing beside of the tracks. Of course, there are different types of masts, and there is a different configuration and different height and so on, as you can see on this engineering drawing. And well, here you can see the ongoing work of our partner of Neom Research. So Matthias Rüther and his group is working here on that. Another object of interest are the rail types within our project. So another partner is working on the detection of the different types of rail. And here are some only a few types of rail used within our network. The difficulty here is that the height differences are very small, so the detection is not that easy. And on this left upper picture, you see the rails that have been detected, and this rail type is marked in yellow. But you can also see a red part here, and this is where the detection was not successful. So, but as you can see on this picture, this is caused by the situation of a level crossing here, and it's clear that the algorithm cannot see the whole cross section of the point cloud data here. On the right picture, you see again this yellow marked rail type and the blue marked track axis. And in pink, you can see the edge of the platform, which is also of interest for us. On this lower series of pictures, you can see the detected change of the rail type. So here, the yellow marked rail type changes into a green marked. You can also see the change here because the sleepers here are of different types. So you have these dark wooden sleepers here, and on the other side you have this light concrete sleepers. Well, that was recent work coming from Taro project. Another project which is also nationally funded is called Rail for Future, and here the vision is that we can build up first steps of our simulation platform. The three parts of the project are on the left side, of course, a kind of data pool where we have asset data, where we have material parameters, behavior models, where we have condition monitoring data coming from sensors and so on. Of course, we need also the training operation data, so for calculating the load, for the wear of the tracks and so on. Then we put all this together with the behavior models into our modular simulation platform. And well, the challenge here will be to aggregate all the results of these very, very detailed behavior models of tracks and switches and so on up to our whole network. And this should be done within acceptable calculation times. So this is the part that we are working on at the moment. And the third part of the project is dealing with the visualization, because if you have got some results of simulations, you have to present these results to the human operator in a comprehensive way, so that he or she can choose the measures that have to be done now. So you see, there's a lot of work to do. We're just at the beginning of our journey towards the digitization of our infrastructure towards a digital twin. And here you can see on the next slide all the partners that are working with us here on this topic. And well, I'm at the end of my talk, and I thank you for your attention.
Well, thank you, Mrs. Haberler-Weber, for this very interesting insight on the demands, the problems and challenges, and also the upcoming solutions on digitization of railway infrastructure, and also the use cases on it. So, having a quick look at the chat, we do not have immediate questions. Perhaps one final question from my side. So what do you see as the most pressing use cases for a digital railway infrastructure? So what will it enable in the short time if it is readily available?
Well, if we concentrate on asset management issues, we are, for example, trying to calculate the optimum time for example, maintenance measures. So when there is need for some maintenance for switches or for some parts of the tracks and so on. So if we have sensor data, if we have a virtual representation of this object, then we can make some predictions and find the optimal time for maintenance.
Okay, thank you on that. Thank you also for this presentation and for your time. If there are questions coming up regarding your talk, I would forward them to you then in sort of a written form, and perhaps we can have an email exchange later on that.
Yeah, so I will stay here until the next break, and perhaps then some other questions arise.
Thank you for that.
Okay, so thanks.
And in this course, we are perfectly on time, and I would now like to hand over to Mr. Wimmer from ASFINAG, our Austrian highway road operator, and give him the stage to give us an insight on digitization challenges on the roadside.
Yeah, thank you. Hi, everybody. Can you hear me? And
perfectly.
I at least can see myself too. So then, and I should share the screen.
I think it's the wrong one. Looks good. Yeah, perfectly. Now you're muted. Yannick, I guess you'll have to, yeah, unmute.
This is interesting. Did you see I couldn't unmute myself when sharing the screen? Okay.
Yeah, this was interesting.
Just a second. Okay, now it should be working again, right?
I don't.
Can you hear me?
Yeah, I can hear you, but I don't see your screen actually.
Yeah, because I had to fix the other problem first. Okay, let's have a look if this works now. It stops my video when I'm sharing the screen. Just saying, but okay, well.
Okay,
maybe
now
we can live with that.
Okay, now I can see it.
And you can still hear me.
And we can still hear you. Perfect.
Okay, but there is no video. Am I right? Okay, then well, let's live with that maybe. If this
and
is.
I do not yet see your full screen. I see the PowerPoint.
Yes,
so
this is true.
Yeah, now it works.
No, you should see. Okay, then let's live with that without a video if this is okay for everybody. Okay, so hi again. My name is Yannick Wimmer. I'm working at ASFINAG at the department, which is doing work on cooperative connected automated driving. And I was asked to give you a short overview over the whole topic about digitalization in road infrastructure, which is a very broad topic. And therefore, let's try to quickly skim through all the topics that come into play. The thing is, why do we at ASFINAG especially at the team where I'm working, think of digital infrastructure, we always think about automated driving. And automated driving is not really a new topic, actually. So when you see here at the timeline, this is something that's actually, well, exactly 100 years ago, there was the first driverless car that made news. And also in the 50s, there were some ideas about autopilot and something like this. But now really there are some technologies that enter the market that become interesting. For example, those highway pilot technologies. And I think many of you have at least once driven a car with some advanced advanced driver assistance already. And yeah, so I think things are moving fast here. And So what's important to understand here is that there is a thing called the operational design domain for automated driving. Actually, for every technology, there's an operational design domain. It means that this is the domain where your technology.
Yannick, I think we lost your audio now. You're not muted, but I can't hear you. Now I can hear you again.
Okay, I didn't do anything. I'm sorry about that. Okay, so where did you lose me?
Like at the ODD.
Okay. Yeah, well, then I'll try. Okay, then it was this slide, right? So
right, yeah.
Okay, so please jump in when it happens again. But I don't have a second screen where I'm clicking anything, so it's really just sorry. I don't know what happened here. Okay, nevertheless, so the ODD is the design, so is where your technology is designed to function. If you leave it, it's not working anymore. And we want to avoid that automated vehicles have ODD breakdowns, because this means that you have to take back control, maybe even very quickly, and this is not safe, and we want to avoid that. And also vehicle manufacturers over time realized and recognized that infrastructure not only can help, but maybe will need to help in the future. This is just one example why, if you compare the infrastructure view, this kind of a bird view, to the vehicle view, you see that the infrastructure might be capable of seeing much more. Actually, this representation here does not even show you that, for example, imagine that if here would be another car, the vehicle would not be able to recognize it, but the infrastructure would, for example. And one very important idea is that infrastructure could expand the electronic horizon by lots of sensor data like cameras, radars, something like this, and expand the horizon. That would be here the green one that the vehicle is capable of doing by itself. But with infrastructure, it can be much wider, and therefore you can react in time to some events. Also, the information about events that are on your path will be, but are very important in this context. But I will come to that later. So the question is, do we need to upgrade our infrastructure? What about support automated functionalities? Main question for me, at least, is which information is needed by the vehicles to fulfill their driving tasks, and can we provide information as a support for those vehicles? Just to give you an example, here is a schematics, a visualization about the track A2 around Graz. This is the best equipped of the ASFINAG network, because it's also a kind of test track for automated driving and other stuff. And here we have, for example, sensors for environmental data, for traffic data, lots of video cameras, even some ground radars. And it's also equipped with CITS community, with infrastructure to vehicle communication, CITS communication, which will be the topic of my talk later on, and I will come to this later on, because this is what we are rolling out currently. When thinking about the automatization, maybe I think most of you have heard about this SAE levels of autonomy automatization. Depends on how you want to put it, where for driver assistance. So basically 2 and maybe also 3 is something that's already more or less in the market. We're getting to 4 and 5, so those are already known as maybe so then as hands off, eyes off, and mind off would be really the full automatization where you could even sleep while driving. This will be some, well, this is kind of far in the future, but level 4, some highway pilots, there are some vehicle manufacturers who claim that there will be some level 4 driving in the very near future. So this is something that might be interesting. And this is why from the infrastructure side, we came up with an scheme that's more or less similar, but due to time reasons, I will go through this a bit quicker actually. But we came up with a scheme where we wanted to classify also the kind of support that infrastructure can give to automated driving. And when you look here, then there is, well, basically on the one end of this scheme, it's called the ISAT scheme, infrastructure support for automated driving. There you have basically no support. And on the other hand, it gets more, well, then, okay, well, let's go through it. You have a digital map at least, which is something that's very essential for automated driving. Then you have at least some D, and it gets better till A, for example, when you really get some dynamic information and when you get some cooperative perception for those who are more or less in the field, then you get better and better in the more and more support you get, the more and more connected the vehicles infrastructure are, the better basically this infrastructure support is. It might be important to know, that's just a disclaimer that I always say when doing this. This does not mean that you need this everywhere. So if you really have, for example, a highway section that's without any curvatures and something like this, and the very easy geometry, you might not need the highest support level. You might need the highest support level there where it's difficult. So yeah, just to wrap your head around this. Yeah. Okay. As I just said before, so one of the main things is a digital map. So this is something that UNEUM does, for example. So I have added the slide here from UNEUM. A digital map, a high definition map, is something that's very important in the digitalization of infrastructure. And here you see you have, I think, Matthias, this is Graz. No, this is not Graz, can't be Graz.
This is
Graz.
Graz.
It says it's Graz Ost.
Graz East,
is
yes.
it?
It's
Graz East. Yeah, it is. Sorry, of course, it is Graz East. Yeah, with with the lane information, with all the information that you have here, and this is very important for an automated vehicle to kind of to have this digital twin, as we already heard in the previous talk. The digital twin, something that's very important for the automated vehicle to kind of match the what's it seeing around with its sensors to maybe some information that it has on board of the digital map. Yeah. When thinking about digital twin, of course, as an infrastructure provider, we are also always thinking about this building information modeling, because ASFINAG is also building a lot and maintaining a lot, and therefore when thinking about digital twin, we also think about digital twins of buildings, not only of, and bridges and tunnels, of course. And maintenance at ASFINAG, by the way, is also done with drones from time to time already, where we scan the buildings, bridges that we have, trying to get digital twins. Yeah. Then you, of course, have to mention the traffic management centers. We have 10 of those traffic management centers at ASFINAG. They have, especially in the tunnels, we have automated event detection and lots of cameras on the network. A tunnel always has to be fully covered by cameras, but even outside, so we have a nearly 90% coverage of cameras on our network. And this is so combined with event detection, this makes it possible to react very quickly if something happens on the network. And also here, next step would be if you would have a really good real-time representation of the network. This, of course, serves the operators as an additional tool to help them. And then we get to the information. Of course, the more complete your information on the traffic event is, the better. And so in Austria, we have the EVIS system. So there's a real-time traffic information system where ASFINAG, but also ÖMTC and the ministry are involved. And this is our approach to, well, to make the available information available as broad as possible. And information that is available here is, well, for example, unplanned events. Well, what is an unplanned event? An accident, for example. A planned event like roadworks, the current traffic situation, or also some traffic forecast. And of course, if you have those kind of information as the end user, as a vehicle, as a driver, it's always it's always beneficial to have as complete information as possible when driving. And this brings me to CITS. So I don't know if you have heard about CITS before. I will ask the question later on. At least I hope so, that you've heard about V2X CITS, because this is something that is actually the rollout of this technology for infrastructure to vehicle communication and for vehicle to vehicle communication has started. There is VW is the first vehicle manufacturer that has it in some of their vehicle models, and we are rolling out this communication technology on our network starting from next year. Actually, our warning trailers are already operational. You'll see that just shortly. And this is a communication, a direct communication, where vehicles will communicate among each other to exchange, well, all kind of information, mainly in the first step, information about potentially dangerous situation and something like this, but also with the infrastructure, and also the infrastructure can give information to the vehicle on a direct path. More on that later on in the specialized talk. But how you can imagine this, for example, in this way, that here you have some traffic jam, and you have roadside units on the side of the road that communicate this traffic jam to a vehicle approaching that might not have yet recognized that there's a traffic jam ahead, which is a great improvement in security, in safety mainly, because we have lots of accidents, unfortunately, on our road where drivers are distracted. This is the main reason actually for accidents on the highway. The driver are distracted and they just don't recognize such dangerous events until it's too late, and then you have a rear end collision. What I meant before with the safety trailer, so we have those roadwork safety trailers, and they are already operational. This is the first thing in CITS that went into operation. And what I have here is a video of driving a Golf 8 VW that is already receiving this warning information via direct, really some direct information. So this is not R&D or something. This is a productive system. Unfortunately, I don't have, and you get this information right beforehand. You don't see the trailer here, but you get the warning, pay attention that there is a construction work coming up. And we hope that something like this will improve traffic safety a lot, because those trailers, we have unfortunately really lots of accidents with those trailers due to distracted mainly truck drivers, but also passenger car drivers. And in the near future, you could imagine, for example, that not only the driver reacts to this, but only that a message like this could, for example, disengage some ACC controller or some, what's tempomat in English? You know what I'm what I'm talking about. So yeah, but could disengage some automated driving function or engage some automated driving function that would help to yeah, counteract if you're approaching this situation. The vision for the future is, of course, to maybe get more and more digital, and maybe such those variable message signs that you know from our roads, maybe in the maybe distant future, we will be able to do all the traffic management, all the work, even without them, because the information could be transported directly to the vehicle. But this is some distant future vision, because of course then everybody has to have some kind of system like this in the car. But this could be very quickly. Yeah, let's see. But let's
Yannick,
see.
I think, yeah. Your audio or again is a little disrupted now. I think it's more of
Depends
a band.
on how fast we think that, at least for the next. Yeah. Okay. Okay. So then I'm already approaching the end of my talk. No worries. So how could those kind of services look like in the future? Well, this is something that's more for the near future, where you basically have actually what we just saw, some kind of warning trailer here that also sends the information for automated vehicle. Well, please change the lane because the lane is closed off, and this might well help for, yeah, also for traffic management in the future. So near future vision, and some more midterm distant future vision would be to have well, at least dangerous, but challenging sections of the network with some high infrastructure support, where you can imagine if you have video and radar sensors here, that you could automatically detect some vehicle that is standing or some object on the road and something like this, and also automatically trigger this CITS warning message that is sent out to the vehicles, and really react basically in real time to traffic situations and help vehicles in real time on the network. Also by detecting really the trajectories of vehicles on the road then, but there you need, of course, some good sensor array to do something like that. Yeah, I will skip through that due to time, but of course, when you have different kind of sensor system, then you need the fusion of those sensor systems to get out the trajectory. But I think this is not so important now. Okay, so what's next? Day 2, CITS services. I just copied you the list here and will not go through them in detail, but you can find something like platooning support. So for heavy goods vehicles, collective perception. This is more or less what I was talking before, just that the sensors give you the traffic situation in real time, and extend the electronic horizon, and something like GNSS correction data. And here we get to the Esrium project, because GNSS correction data is something that's very important in the Esrium project. One of the key factors, one of the use cases actually. And to conclude, so of course, the conclusions are a bit CITS specific because, yeah, this is what I will be talking later on in the second talk. But CITS is an open communication channel for traffic-related information between the vehicles and the infrastructure to increase the traffic safety. We have seen that CITS day one is already a reality on our motorways, and the roadside units will be rolled out, and construction site warning trailer is already there. We will also equip our operating vehicles actually with this technology. So the traffic manager vehicle of ASFINAG. And in the future, we plan on having traffic control and, well, those use cases that I was showing you before. And there are numerous R&D activities on this topic ongoing with regard to CITS, but with regard to also some other digitalization aspects that I was showing you in this presentation. One example being the Esrium project. And this concludes my presentation. Yeah, due to technical difficulties, 5 minutes longer, sorry. But yeah, are there any questions?
Thank you for this good insight into the digitization problems of road infrastructure. So, yeah, I do not see immediate questions now, but I think there is time for.
There is one question I see in the chat, but I have to admit this is more for you actually. It is what is the map format for the HD map that I was showing?
Right. So
yeah.
Patrick Lula already answered it in the chat, I think.
But, yeah, I see. You're right. Yeah, I see.
The provision of this format comes in a variety of file formats. So we are using Open Drive, which is a quickly evolving standard in this field, but also like publicly known GIS formats like GeoJSON and shape files, and also simulation relevant formats like the Road5 format. So we are quite open here. And I think there will be a convergence of the whole industry to specific formats, which will be Open Drive and the well-known GIS formats in the end. So Yannick, perhaps a last question for you from my side. Also regarding communication and CITS, who do you think will be the early adopters of this technology? Will it be like trucks and logistics, or will it be premium cars, or will it come to everyone via sort of a standard? What is your opinion on that?
Well, yeah. So interestingly, it's now it's in passenger cars, but actually I think this really has the potential for a kind of disruptive technology, to be honest. So it's more or less I always compare it to our mobile phones, basically, right? So some 20 years ago, nobody had a mobile phone, and now everybody is surfing on the internet with their mobile phones, and we think, how did we do before? And I think also CITS has this kind of technology this kind of potential to be a disruptive technology for all kinds of vehicles, because this is something that might be really an essential service. Another comparison is it might be a step as big as the introduction of is ABS is the German word for how do you call it, your braking system that avoids that your brake really
the anti-blocking system.
The anti-blocking system, yeah. So it might be a technology like that, hopefully, at least, yeah. Yeah.
Okay, so thanks again for your talk. We have used now our coffee break also for Q&A, but I think if everyone is fresh enough after 1 hour, I guess it's a good point that we continue right away with our next session. And thereby, I would give the stage to Manuel Walch, who will present a selection of use cases for digital infrastructure twins. I will also ask Manuel to give us a hint when to start a specific poll in his talk, so that we can interactively collect feedback from our audience there. So in this course, Manuel, the stage is yours.
All right, thank you very much. I hope everybody can hear me.
Perfectly.
Sorry to interrupt you. Just a short note, Matthias, maybe it makes sense to copy the link for the polls once again into the chat so that it's available for all.
All right. So I will do this right away and in parallel. Yes.
Perfect.
Perfect. So, all right, let's start with the presentation. So, well, hello, everybody. My name is Manuel Walch, and I'm a researcher in the field of logistics at the University of Applied Sciences in Upper Austria. Our team focuses on hyperconnected logistics systems, and within this field, topics like CCAM or CITS also play an important role in our research. We are currently working together with international project partners on the Horizon 2020 project Esrium, which, as Matthias mentioned earlier, stands for EGNSS-enabled smart road infrastructure usage and maintenance for increased energy efficiency and safety on European networks. And today I would like to present the use cases of the Esrium services that were formulated in the early phase of the project. Before starting our presentation, I would like to point out that, as Matthias mentioned earlier, that there will be poll questions during and after this presentation, and I would very much like to encourage you to take part in answering these questions, as feedback to these matters is highly appreciated. So thank you very much in advance. And all right, I think we can start with the presentation of the use cases now. So before I go into more detail about the use case development and their detailed description, I would first like to give you a brief overview of its function in the Esrium project and its influence on the further course of the project. So as you can see on the slides, the definition of the use cases is the first task of our work package 2, which is called use cases and requirements analysis. And as can also be seen on the slides, the formulated use cases then serve as kind of a basic building block for further tasks within the Esrium project. Especially in the further course of work package 2, they are used, for example, as an input for the formulation of technical and non-technical requirements and for the system interface design, as well as for the creation of business cases. In addition, the use cases are also applied in the remaining work packages 3 to 5, as they are taking the use case description, the technical and non-technical requirements, as well as the system interface design as a starting point for the work. So, well, first of all, let's take a quick view at the methodological approach we used to develop the use cases. Well, as different stakeholders need to be considered when formulating use cases, like, for example, end users, original equipment manufacturers, and road operators, a methodological approach was required that takes into account the needs of all of these different stakeholders. So based on the project proposal, our team performed a use case analysis to develop a detailed description of the services that can be offered by Esrium. And within this analysis, 4 different application scenarios of Esrium services, including their potential target groups and application requirements, as well as the respective challenges were defined and developed. This until then internal view has then been validated with our key customer, which is the Austrian road operator ASFINAG, and the integration of their related feedback in an advanced version of the use cases. Another internal validation process with all the project partners took place to develop kind of a consolidated consensus within the diverse team of Esrium. One of the main advantages of the Esrium team is that the coverage of different parts of the necessary value chain, including the potential customer and road operator, which is in this case ASFINAG. And furthermore, obtaining external feedback from ASICAP confirmed the relevance and the importance of the respective use cases, which is also stated in the ASICAP CITES manifesto. All right, let's move on to a detailed description of the use cases. Here you can see an overview of our 4 use cases that we have developed and how they are related with each other and the relevant stakeholders. The first use case deals, for example, with AI-based road damage prediction. Use case 2 then deals with routing recommendations. Use case 3 deals with the provision of EGNSS correction data, and use case 4 deals with the provision of a roadware map. We will have a look at into all of these use cases in the next minutes, but due to time constraints, I will not go into detail of this graph, as most of the relations will be addressed in the following description of the use cases. However, if you are interested in more details, you can find more information in the deliverable on our Esrium website. All right, then I would suggest that we proceeded to the description of the use cases and start with use case 1. So this graphic shows the first use case, which deals, as I mentioned before, with AI-based road damage prediction to support enhanced road maintenance planning. So the target group here is the road operator, and according to the road operator ASFINAG, motorways in Austria are currently only surveyed and checked for road damage every 4 years. And this leads to, on the one hand, high costs because of long-term construction sites that could be avoided or greatly shortened with earlier diagnosis and or appropriate preventive measures. And as part of the Esrium project, a digital twin of the road is created through a regular road damage surveys, and the position of all road damages is measured precisely at centimeter level. Based on this developed road sensing and damage mapping system, a roadware map utilizing AI-based road damage predictions will be developed and provided to road operator. And based on the predicted onset of road damages, the road operator can then derive predictive road maintenance and action plans to proactively avoid and or reduce more severe road damages. The preliminary pain points of this use case are that the measurement of motorways in a 4-year cycle results in high costs, as road damages are discovered too late and long-term construction sites are necessary. They in turn lead to a deterioration in traffic efficiency and higher CO2 emissions. Other side effects are an increased risk of accidents in the roadworks area and a rising road user dissatisfaction due to for example, traffic congestion. And Esrium services improve, therefore, the safety, effectiveness, and environmental footprint of road maintenance by identifying these kind of road damages early and taking preventive actions sooner. This in turn reduces the average duration of roadworks, decreases congestion and CO2 emissions, and reduces the cost of road maintenance. All right, moving on from use case number 1, use case number 2 then deals with routing recommendations. So, well, as I said, the second use case deals with routing recommendations within and between lanes based on the roadware map, which are sent into the car via CITS messages by roadside units. The target groups in this case are end users, for example, drivers of automated trucks and passenger cars, original equipment manufacturers and logistics operators. And based on very early damage prediction, the road operator can then derive an enhanced action plan to proactively avoid severe road damages. One of the actions is, for example, to provide EGNSS-based lane change or in-lane offset recommendations for the drivers or end users in general, in order to avoid severe road damages and critically safety-related situations. In this scope, user compliance-based incentive concepts will also be investigated. For example, road users, especially in this case truck drivers, could receive, for example, a toll reduction for complying with the in-lane or the between-lane routing recommendation. These routing recommendations will be tested on our test tracks Alplab and Digitizing with automated vehicles and conventional vehicles. And well, furthermore, it also has to be mentioned that route recommendations within the lane are only carried out by automated vehicles with the corresponding sensor technology, as an exact in-lane offset by a few centimeters is only possible with the corresponding technical support. Well, within this use case, it will be considered in the course of the project whether the existing advanced driver assistance systems of vehicles are already sufficiently compatible for the reception of CRTS messages, or whether costs for the additional acquisition of onboard units are to be expected. Furthermore, it has to be considered that the specific vehicle characteristics, for example, the width of the vehicle, are not available for broadcast services, and only generic routing recommendations can be offered. And additionally, the routing recommendations must be communicated to the driver in a way that does not distract him or her from driving, kind of to a similar extent as navigation systems. So the security risk associated with receiving and interpreting CRTS messages is therefore an important factor to be considered. The goal of this potential Esrium service is that the driver feels both safe and relaxed, and that the system is effective. So, and this is the only way to achieve sufficient user acceptance for the routing recommendations to prevent severe road damages and to ensure a more even wear of the road. Next, we will have a quick look at the use case number 3, which as use case number 1 will be an influential part of the use case dealing with routing recommendations. So use case number 3 generally refers to the additional use of EGNSS correction data for more accurate vehicle locations. So the road operator again provides EGNSS correction data to the end users via CRTS message from roadside units to improve the positioning accuracy of the end user's vehicle. And additionally, the vehicles which are carrying the sensors for the detection of the road damage in the first place they also use this service, as the road damages can then be mapped on a centimeter level to the respective road network. For original equipment manufacturers, this service is relevant for optimizing their advanced driver assistance systems, for example, the lane assistant or the cooperative adaptive cruise control. The relevant stakeholders in this case would therefore be, on the one hand, end users, in order to be able to avoid road damages, and on the other hand, original equipment manufacturers for optimizing their advanced driver assistance systems. The provision of EGNSS correction data is necessary to ensure that the vehicle position is determined as accurately as possible. So if the vehicle position is lost, for example, the advanced driver assistance systems such as in-lane offsets would not work correctly, which would in turn also increase the safety risk and potentially cause accidents. Furthermore, these accidents would then also potentially lead to liability costs. So with DHNSS correction data, appropriate safety is ensured, and the lane change or in-lane offset adaptation recommendations can then be carried out more accurately and with improved safety. So the accuracy of the vehicle location is, as mentioned before, on a centimeter range, which allows following the lane change or in-lane offset recommendations accordingly. And furthermore, providing DHNSS correction data via CRTS also acts as an additional source of correction information and adds redundancy. So therefore, this system also meets the functional safety requirements for automated mobility. Well, so much for use case number 3. We will now get to the 4th and to the last use case. So the last use case deals with the where map content provision to the relevant stakeholders, which in this case are navigation service providers, original equipment manufacturers, and road operators. And based on the developed road damage detection and mapping system, these stakeholders are provided with the road where map. And in addition to general information purposes of road damage recorded at, as I said before, the centimeter level, this can also be used, for example, to give routing recommendations or make route selections. As a driver, for example, I can select the most comfortable or convenient route to drive on. The biggest pain points identified here are, for example, the traffic safety risks due to construction works or the safety risks due to damages on the road surfaces. So the road wear map, on the other hand, might increase the driver convenience and traffic safety by proactively avoiding road wear geolocated in the roads wear map layer. The general focus here is also on the compatibility of the data in order to reach the broadest possible mass of road users. And furthermore, the maps need to have an appropriate accuracy and receive regular updates to ensure meaningful use in practice. All right, that has been a quick overview of the use case we developed within Esrium. And as I've mentioned in the beginning of the presentation, we have prepared also a few poll questions based on the use cases that we would ask you to answer. So the first question would be, how would you rate the importance of GNSS-based use cases for predictive road maintenance? The second question would be, how would you rate the acceptance rate of truck drivers to CRTS messages like recommended lanes provided by road operators? So do you think that truck drivers would be willing to comply with such lane change maneuvers in the first place? And the last question would be, how would you rate the importance of benefits like reducing tolling for truck drivers' acceptance of CRTS messages like recommended lane changes provided by the road operator? And as I said also earlier, we would very much appreciate your thoughts on these questions. All right, that's about it for the use case descriptions of the Esrium services. If there are any questions, I'm more than happy to answer them now or later in the chat, or if you want via email. But as for now, thank you very much for your attention, and I'll be giving the floor back to Matthias. Thank you.
Well, thank you, Manuel. So I opened the first poll question, and I will leave open this question now, say for like 2 minutes, and then switch to the next poll question, and then to the next. So please participate in the poll. In the meantime, regarding questions, I don't see immediate questions here. Let me share my screen again. All right, now we are right in this talk with a few minutes left. So regarding the polls, I suggest I keep them open in the meantime, parallel to the next session, so everyone can then has enough time to add the answers there, and we will discuss the results then in the closing round at around 12:30. All right, so in this first talk, we got now a good overview on what use cases of such a road damage, digital twin of road damage can be.
The fuck you say to me, you little shit? How are you not in fucking school? You kiss your mother with that mouth? Your mother with that fucking mouth? Huh? Huh? Because the fucking youth of society.
Where did we get bombed here? Okay, so I hope we can continue now and everyone hears me again. After our use cases, we now jump right into the technical details on how to actually gather such a type of information and then how to administer and distribute it. And the first talk on this will be about sensor technology. It will be given by Richard Ladstätter and me, both from UNM Research, Institute Digital. And based on that, we will have additional poll questions also running in parallel there. So thereby, I would like now to give the stage to Richard. Please start with the presentation and I will jump in the second half of it.
Okay, can you hear me?
Yes.
Okay, so I will share the screen, okay? Okay, so hello to everybody. I will start this talk about sensor systems we use in the Esrium project. Actually, you can see this mobile mapping system we operate here at UNM Research on this picture. This is a survey-grade instrument we use in various projects here. The railway project Taro was mentioned already, for example. And with such a system, we can generate very high quality point clouds and imagery of roads by just driving them and taking pictures and doing laser scans. You can see the system has 2 laser scanners on it. They are very accurate. They generate very dense point clouds. And also you have very precise navigation units on the system. So you can locate everything you measure very precisely on the road. So we use the Pegasus system from Leica. You can see it here on our car. You see a lot of cameras, 2 cameras at the back, they are pointing to the road surface. And this in this project Esrium, this is used to map road damages on the highway. And you can see the accuracy is about ±5 centimeters at least. If you have open sky conditions like it is usual on the highway, you can even reach ±2 centimeters accuracy without any additional control points or anything else. So this is a very sophisticated system, and it provides all the basic data we use for mapping and producing these UHD maps you have already seen in all our projects. Our Finnish partner uses a mobile mapping system. You see it here. on the picture. They have designed their system by their own. It uses another scanner. It uses one panoramic camera, but the basic principle is the same. So it's a mobile mapping system. You can drive the road and collect all the data you need for road damages, and also the accuracy is about the same. By the way, this is called Roma, this system. So this system is used in Finland, and we are using our system Pegasus in Austria. And we have defined some test areas in both countries to collect some what we call ground truth data. So we have, this is a kind of reference data you are using to train software algorithms later on. So Matthias will talk about that. You can see in Austria, we are here at the area of Graz. We use basically we are driving the highway A2 and A9. They are crossing right in this region near to Graz. And in Finland, there's another test area defined, which is a road. It's not a highway. It's you have some lower speeds, but it's very far to the north. So you have other problems with the weather conditions and so on. So this is two quite different test sites, and this will be interesting to compare results from these test sites. Okay, I've just just want to show you some examples from what we got so far in this project. You see, this is some data from the Pegasus system. What you get from these pavement cameras. You see on the left side, you see some cracks and some detachment on the surface. In the middle, you see some kind of pothole. It's quite deep, so 7 centimeters deep. You can get this information, for example, from the laser scanner directly. And you also get some, you see some fine cracks in asphalt, in the asphalt surface on the right. So this is just 3 examples what you can see from this data. And of course, all this data is georeferenced very accurately, so you can really locate this pothole exactly where it is, on which lane, on which road. Some samples from the Roma system. You see here scan data and some profile cross sections through this data, where you can clearly see these road damages, and you also see to the right side, you see the panoramic image, and this is typically what you get from mobile mapping. You get laser scan data and image data, and the combination of this information will provide a very good training data for our second system, which Matthias will now present. So Matthias, I will hand over to you right now. Okay.
Yeah, thank you. Please keep the presentation open, and I will just then ask you to jump to the next slide so that we are consistent here. I will just open another question on our poll, so we continue our questionnaire here. I see there is much activity going on, so thank you for the feedback there. All right, so next slide, please, Richard. So what we have seen so far in this presentation is there are numerous really survey-grade scanning systems which can actually gather information of the road surface in good resolution and also good geolocalization. But of course, they are costly, and therefore they are hard to deploy, say, on a larger scale. If you really want to have a digital twin which is up to date for, say, an entire national road network or even a European high-level road network, then you would need many of those scanners. So one of the basic major research questions here is, can we make such systems more cost efficient than with survey grade systems? Can we do it cost efficient? Can we do an efficient data transfer so that finally we have a system deployable on a vehicle fleet, so that not only a single individual scanner is operating on several thousands of road kilometers, but multiple cheaper systems can go actually with routine drives of the road operators, can operate routinely on the road network, and therefore impose little additional costs for data acquisition. So next slide, please. Thereby, we have set up such an experimental system. It actually consists of several sensor systems. It has two automotive grade LiDAR units on board. Actually, Richard, please go back one slide again. Thank you for that. Here you can see the experimental setup. So what we have here is a system consisting of cameras which actually surround the vehicle. So there are 4 cameras providing a 360-degree view. There are LiDARs, automotive LiDAR systems on it. There is a stereo system on it, which provides synchronized images of a distinct part of the road. And there are, for research reasons, several IMU systems on board. So a high-grade IMU, a fiber optic IMU, and a smaller micromechanical IMU for comparison of localization accuracy. Next slide, please. All those components, of course, are modular in the mounting, and they are synchronized. They allow for a concurrent data capture in the vehicle. They are triggered in a synchronized fashion, so that the scanning type scanners like the LiDAR trigger the cameras. So as soon as the LiDAR beam enters a certain camera field of view, this specific camera then also is triggered. And therefore, there is little offset, temporal offset between 3D points captured by the laser scanner and 2D pixels captured by the camera. There is also a computer system attached with 3 compute nodes in there. So we have basically 3 PCs added to this sensor platform. So we can do real-time data capture, but we can also do real-time data processing, especially encoding and compression, so that we reduce the actual bandwidth which will finally be necessary to transfer this information from the vehicle to sort of a central data platform. So now I can give you a few qualitative results of what this scanner can actually see on the road surface. So here you can see a first qualitative evaluation of automotive camera systems and LiDAR systems on the road surface. Because we are envisioning a operation, a routine operation of such vehicles on the road, we cannot go too slow. So we need to go at least with 100 kilometers per hour, such that we do not pose a safety risk or cause traffic jams or other issues on the road. Here you can see a result from those 12 megapixel cameras we have put on there. Those are modified in several aspects, so they are also sensitive in the infrared range, in the near infrared range of the spectrum, so that we increase sensitivity there. What one can see, the detail is sufficiently high to resolve issues like cracks or repaired cracks on the road surface. We have some motion blur, but not too much, and we deem it feasible to use this camera information for automated damage segmentation and also for like stereo processing there. Okay, next slide, please. Here you can see a road damage captured with the same system at 100 kilometers per hour. This would be a repaired pothole with outbreaks. So it's a damage which has been repaired and has evolved again. So something very interesting for us. And one can also see, one can resolve this issue with the camera. One can at least capture it and then provide it to a detection system. Okay, next slide, please. Here one can see an exemplary stereo reconstruction. So here we are using both cameras, left and right cameras of the stereo system, do a matching, and then a 3D reconstruction of the surface. And what one can see here, one can get a very subtle height offset. One can resolve this with the stereo system. So by the pure eye, it is not really visible that this patch of asphalt on the top right has a different height than the other ones. And the stereo system can actually resolve that. And here it has a much higher height resolution than, for example, the automotive grade LiDAR, which only gets a height resolution of several centimeters, and thereby will not be suitable to reconstruct such subtle height differences here. Okay, next slide, please. Well, now I'm coming to a summary. So what we have found out by our initial experiments with 2 mobile mapping systems and 1 experimental setup with lower grade sensors is that clearly the survey grade LiDAR systems deliver a local accuracy which is sufficient to resolve the road damages we are dealing with. On the one hand, with the laser scanner, which delivers also local accuracy in the millimeter range. The global accuracy, of course, will be worse, but this will not affect our damage detection, actually. And the high resolution images typically also have a very good image quality, but of course, in mobile mapping systems, they are typically tuned to a different application. So they have a more narrow field of view. It will be hard to cover like the driving lane and the neighboring lanes with the cameras themselves, if one doesn't take a huge additional investment. In contrast to that, the lower grade system with automotive sensors regarding cameras and LiDAR also show promising first results. So the LiDAR will actually not be capable of resolving and measuring those very subtle and small geometric defects, but it can capture large distortions like ruts on the surface with the LiDAR alone. Stereo reconstruction is a complementary technology there and adds higher depth resolution. Of course, at a certain cost. The cost is especially in the computational power required to finally do the stereo matching and stereo reconstruction. The cameras by themselves can resolve the road defects at sufficient detail, and also with a good auto exposure method, they can operate also at those high speeds above 100 kilometers per hour. Okay, so this brings me to the end of our talks here. If there are quick questions, we are happy to answer them right now, and otherwise we will address them finally in the closing session. So thank you for your attention. Are there immediate questions from your side? I don't see immediate questions in the chat. So since we are right on time for the next presentation, I will hand over immediately then to Andrzej Czegiński from NNG, and to give us a short introduction on how to finally manage this sort of information and provide an interface for a further distribution of it. So
thank you
Andrzej,
very much.
the stage is
Thank
yours.
you very much, Matthias. I hope everyone can see me, and I will share my screen also. Hear me, see me, and see my screen. Hold on.
Not your screen, but you are fine.
Now you shall see my screen.
Yeah, now it is here. Thank you.
Excellent. Thank you very much. So Matthias, thank you for this nice introduction, and thank you very much for the previous presentations, because what I will show here, it's a little bit of the central element of the Esrium project, where we are aggregating, where we are putting all together the information and providing it to the users. So therefore, I would like just to give you the concept and the status of the data platform, and you will see how I try to interpret in a way, on a holistic way, not excluding all the necessary features to be explained, meaning the data, the dynamic data, the statistical data, and all the different aspects. So in order to be very much on the safe side, we have to take into consideration the system components, and in the system components we have to identify where this data platform, or at least several data platforms and several features and several functions which serve the purpose of this unified data platform concept are situated. So what we call as data platform consists of the data management platform implemented by Joanneum Research. This brings to us to the next element, which is integrated into this very same data processing step, which is the prediction system, because we provide also prediction in future projection of the evolution of the roadware roadware features. So it is provided by Evolit, while the data service platform, the actor, the role which serves the end users, provides the service to vehicles, to road maintenance facilities, is implemented by the data service platform developed and provided by NNG. So this will be the scope of our discussion. But first of all, I would like just to highlight and give you the overview and the goal of the data platform. Map data storage for delivery is key element. And for that, we have to have a flexible and scalable solution. The aggregated, verified, and validated data of the roadware condition has to be stored a way which provides, ensures interoperability. So standard data formats and standard interfaces shall be implemented. That is the one of the most important message. And I will try to highlight this very specific aspects later on. So let's start with the data management platform. The data management platform situated at the beginning, aggregating information coming from the sensor systems, and also providing information to prediction system and aggregating output also from prediction system. What is the purpose of the data management platform? So it stores roadware map features and roadware prediction with metadata. This is one of the very key and very basic feature of the data management platform. It also aggregates different types of roadware hotspots as special features. It is important. We are dealing with spatial data, georeferenced spatial data. It is implemented as spatial database with time series support. Also, it provides management, validation, and visualization models in order to make these data verifiable, make it validated. It has to be done, otherwise the result wouldn't be trustworthy. And it has to provide interface for uploading and querying data. So these are the basic features. So what is the data source? From this data platform gets information. So these are the roadware sensor systems. We just showed these systems, sensor system, thanks to Matthias. And the ground truth data, meaning that the very sophisticated data collection device, which is providing information on HD for HD map, so creating the digital twin of the physical infrastructure. Target end users. All these information are needed by road operators. Will be needed by road operators, fleet managements, individual drivers, and so on. So a number of other use cases can be developed. We only target today 4 use cases, as it was explained before. Output data formats, we have OpenDrive 1.4, version 1.4, and GeoJSON. So this is what we will get out from this system. Now, we have the basic understanding on the data management platform, but we've been talking about what it represents. So it is important to see that perceived roadware features are stored using unique IDs, identified, classified. It is also represented by polygons, polylines, etc. And also it has its unique timestamp, because it is important for prediction. We have to have timeliness in the data stored. Also, it provides a classification, so the severity. It provides also a kind of features like how much water can be accumulated in the given roadware features, and also there are a number of other attributes and metadata which will be extremely useful for later use. Now, I've been already talking about this prediction system while we are doing that. The prediction system is important because it is not only giving us an impression that, okay, we have actually a problem here, but it will provide us at least a kind of projection, how it will look like in given time frame. So it is very important. For that, we have the prediction system implemented by Evolit, where the main features are the following. This system provides roadware and quality prediction based on the time series of the classified roadware data using artificial intelligence, machine learning technology. It provides also a description and depiction of road performance indicators with suitable deterioration models. and reliable calculation approaches and forecast models with clear connection between time-dependent and mechanical parameters, as well with other influencing variables. Yeah, it is very complex. You know, this is already future technology. This is already implementation of artificial intelligence in mobility, and that is where we are entering in tomorrow. So far, so good. The data source is from the data management platform. The target end users are road operators. Road operators will use this data to program and optimize their road maintenance activities. In order to do that, we will need, of course, the necessary information, which will be provided using GeoJSON format. Okay, so we have this very important element already clarified. Now we enter into the also very complex delivery or service platform. The data service platform is indeed the connection point of our system to the end users, to the users who will make use of the data created by all these data value chain. And for this, we have to be very cautious and very careful while defining all the necessary data, all the necessary interfaces. Why? Because otherwise interoperability and usefulness of data will be just not possible. So the data service platform main features. So it provides services based on the classified roadware data, prediction data, and map data. So we have all these different layers on top of each other. And these data from different sources are map matched and geo-referenced. So it is very important to understand that everything will be on the right position, on the right section of the map. Roadware and prediction data are aggregated for road maintenance purposes. So therefore, we will need to have an interface to the road maintenance services of the road operators. We will have also a kind of trajectory recommendations, which are calculated for passenger cars and heavy-duty vehicles according to the requirements of the road operators. So we will also implement the guidance and requirements of road operators for those who are using their infrastructure. And of course, it will convert map and roadware data to different guidance services, such as NDS Live, Cooperative ITS, IVI, in-vehicle information services, or even TPEC2. Roadware provisioning is a huge potential for future services. Now, let's look a little bit inside this data service platform. The data source is, of course, data management platform. They are those who are doing all these data aggregation, data verification and validation, and also integration of prediction data. So these data sources will be, at the end of the day, be the source of information. The data formats. So we will have an HD base map provided by the data management platform using OpenDrive 1.4, which will be converted to NDS standard using NDS standard. Most probably we will have NDS Live potentially, because we have already the working solution. And the classified roadware data and prediction data will be provided as ASN.WAT or XML, but any kind of other dynamic data standard can be supported. So GeoJSON is a flexible source format. We can transform it to whatever the requirement is. In this case, we will use ASN.1, ASN.1 being the data serialization format of Cooperative IPS. So IVI service is using the ASN.1. Now let's see what are the different interfaces. So we have the road maintenance interface. It has the purpose to deliver information for the road maintenance database of the road operators in order to aggregate the classified roadware data and provide the road surface quality data to the road operator. In our case, this is Asfina. So we will need to use the requirements and the specification they are using internally in their database, and we will need to implement at least support the classification schemes of the road operators. Well, this is one of the really interesting challenge what we are facing of, but of course, as you can see, it has all the necessary information to be implemented. The next interesting element, interesting interface, optional interface actually in Esrium is the map service. Map service is, it's a kind of navigation, in-vehicle navigation support, where we are providing the map data, static and dynamic data into the vehicle. So while we are doing that, we may do that using NDS Live Service, using the smart layer path methodology. We can provide it as defect 2 for dynamic data. Again, this is only dynamic data, but these are the options how we can propagate information. And again, this is also something very well specified by industry stakeholders. Another very interesting interface is the so-called routing interface. This routing recommendation coming from the data service platform is using the road operators cooperative ITS IVI service. IVI service is implemented by the different ITS station units, roadside units. But also we will need to provide the accurate information according to the standard 19321 of ISO. And the target users are passengers, cars, and heavy-duty vehicles, trucks, and buses. It can be human-driven or automated vehicle, and also these are making the difference between what we provide them as a recommendation, because of course different type of vehicles needs different kind of recommendations. Possible recommendations are avoid road damage by an in-lane maneuver, so meaning that we need to push the vehicle to the left, to the right, from the actual itinerary, actual path in order to avoid a road damage. Or if the road damage or the vehicle type makes it necessary, we have to make a lane change. So it will be the recommendation, please change lane. There is another option that if you cannot change, if you have not the situational possibility to change lane, or even to make this in-lane maneuver, then please slow down in order to keep your vehicle and the traffic safe. So these recommendations will be implemented using the CITS IVI specification, where we will use all available information: road damage, position, and severity, vehicle type. Actually, we will have these two categories: heavy-duty vehicles, buses, and passenger cars, because of the actual limitation of the standard, and also the speed limit. So this service will be one of the most important in this regard, because it impacts traffic safety. It impacts also vehicle moving vehicles. Therefore, it is the most important and the most interesting in this project. So, to give a summary, a conclusion, what we have said so far, the Esrium data platform is a multi-stakeholder, very complex system, which includes data classification, data aggregation and validation, prediction mechanism, data serialization, data delivery, and which has to be implemented on a way which is standardized to ensure interoperability. Actually, the status of this data platform is in the design and specification phase, where, as you could see, we developed the necessary use cases. We are finalizing technical and non-technical requirements. So the data platform is under specification right now, but it is very much on the good way. And I hope the next time I will be able to report you what we have done, how we did it, and what are the results. I think this is my last slide. Matthias.
Thank you, Andras. Thank you for this overview on the challenges of data management, because capturing the data is one hand, but then exploiting the really relevant information and also distributing it is at least as high of a challenge. So are there immediate questions on the talk? Well, then let me put a last question to you. So regarding the outcomes of this project, and regarding considering that we will have sort of a road damage layer, do you see an option to integrate this information into already existing map informations, like they are present in navigation systems and so not only automated systems but also standard systems?
It is a clear need. It is a clear need to have this information, because if you are just looking at proprietary systems such as Waze does it on the basis of community data collection, and many drivers are extremely keen on having all this information, mainly because this impacts physically their vehicles. If you drive 90 km/h in a pothole, then you may have your tire exploded, you may have your wheel completely destroyed. So I think this is a valid use case, not only for automated vehicles, but actual drivers, actual navigation systems, actual navigation system providers. For me, this is something that has a potential business value from the beginning. So it is really interesting for everyone. More precise data we have, better service we can provide, and I think this is very much interesting for all the stakeholders, you know, being keen on road safety and traffic safety.
Thank you on that. There has been a question now also in the chat. Is the data semi-structured or unstructured? I'm not really sure if I get the question.
I think I think I tend to understand it. So semi-structured, unstructured. It's you know, it's like the weather information. It's like, you know, dynamic information coming from all this changing environment. It is the data itself has to be structured, otherwise it makes no sense. But it has to reflect the ground truth. It has to reflect the physical environment, meaning that, okay, I have the data in a geographical location. It has to have a clear data structure according to the standards, the data standards we are using. So it's very important to understand that in order to make the system already interoperable, or to have the concept interoperable, every data has to be created and made provisioned on a standardized way. So, you know, GeoJSON is standardized. I mean, this is IETF, but this is a standard. So we will do everything to make as structured and as standardized as possible. I hope this answers the question.
Thank you, Andras, for the answers. We now have a 10 minutes break on our agenda. We are quite well on time for that. So I suggest we do this, and we meet again for the last session at 11:40 sharp. So thank you, and we will have a short break now. Twin about the sensor technology and also data gathering and data distribution. We come to very specific aspects, which is then feedback to potential users, especially via CITS. And there, I'll give now the stage again to Yannick Wimmer from our Austrian high-level road operator ASFINAG. Yannick, the stage is yours.
Hi, can you hear me again? Okay, let's see if it stays this way. Okay, if it stays this way when I'm sharing my screen, let's have a look. Okay. Okay, it's okay. It's doing something, but it takes some time. I don't know why.
It's not going up.
Yeah, it's just I don't know what's wrong today. But
Yannick,
okay,
shall we share your screen or the presentation?
Can you still hear me?
Yes.
Or am I okay? Because I have, it's just I have the whole screen is grayed out at the moment, and it's not responding. This is something new. Maybe I have to re-enter the Zoom session. I'm very sorry. I don't know. So why Zoom makes so much problems today.
Yannick, maybe Matthias can run your presentation.
Well, yeah, okay. Well, he could, but I can't see it because my screen is grayed out, and already I added some more slides. To be honest.
Okay.
Yeah. Well, give me. So you're not seeing anything now. Well, let me just re-enter. I think that's the quickest way. Sorry about that.
Way, yeah. So
yeah.
See you soon. Now you're here again.
I'm back again. Yeah, it might be that I can't install Zoom, so I'm always using the web version. Might be that this is the problem. I will switch off the video again. Maybe this causes the problem. Let's see.
Okay.
Okay, now it seems better, right?
It seems better, yes. Yeah, here's your presentation.
Okay, okay. Yeah, sorry about that. I'm doing my best. Okay, so CITS. We've heard a little bit about CITS before. You've seen this slide already. So just to recap, it's about the vehicle-to-vehicle communication, but also communication between infrastructure and vehicle, both directions. And it's based, it's the thing that we are rolling out is based on a Wi-Fi standard, but there's a slide on that later on. CITS means Cooperative Intelligent Transport System. So why cooperative? It means that you have an open channel, and via this open channel you exchange safety-related information and other information, but in the first step mainly safety-related information between the vehicles and between, well, all the participants, all the stakeholders, if you want to put it like that. And second important part is that it is a direct communication path. So especially when you're communicating directly via the roadside units, then you don't have any back end of of any cloud operator or of any, well, maybe cloud of a vehicle operator in between. It's a direct link to whom you're talking, a direct link between the vehicles also. And this is what makes it very fast. Yeah. And yeah, and this is what I said before. So in the rollout in the technology that we chose, it's a Wi-Fi. Sorry, this is the German word. It's a Wi-Fi standard. This may sound like internet, but actually it's something completely different. You will see that at the end of the presentation. So as I said before, just to recap, there are three things. Infrastructure to vehicle, which is what we will be looking mainly in this presentation now, but it's also vehicle to infrastructure. So if the vehicle sends information to you, and it's also vehicle to vehicle. How can you imagine this? Well, you can imagine this as you've seen before. For example, that there is the roadside unit warning you of some traffic congestions before, and this would be a vehicle to vehicle or a vehicle to infrastructure use case here. For example, when you have an accident, the vehicle tells everybody, I think I've had an accident, tells this to the infrastructure, also to the vehicles around, but also the infrastructure could again disseminate the message. So this is all at once, if you want to put it like this, all kinds of pathways. And then let's jump into this section a bit more, because when I'm into this topic, when I'm talking about CITS messages, there are different kinds of CITS messages. In that way, so basically there are even more than that, but let's talk about those four that I have on this slide here, because I think you get a good overview of the CITS messages there are. So there is the come message. A come message is really, you can imagine as a kind of, it gives the position and the speed and the heading of the vehicle. So it tells everybody else on the road, here I am, and I'm going there. And so to raise awareness that you're here. So therefore, cooperative awareness message. I think this is quite easily understandable what the come message does. Then there is the so-called decentralized environmental notification message, a DENM message. Think of it as a hazard warning, because this is a quite long name. Think of it as the hazard warning. Basically, not entirely true, but nearly true. You can say everything that is a triangle sign would be a DENM message, because this is mainly hazard warnings. Can be the accident example before would be a DENM, but also for example, also roadworks would be some adverse weather conditions. If something is, if there's an object on the road, something like this would be the DENM message. And on the other hand, there is the in-vehicle information. So this is more for all kinds of information message that's not a hazard warning, but it can be regulatory too. For example, a speed limit would be a classic in-vehicle information message. But basically everything else where you have a road sign, you can communicate via this in-vehicle information. And there is something that's not so relevant for ASFINAG actually, because we don't have that many traffic lights on our network. We have them on the tunnel entries, but that's about it. But for road crossings, especially of course in cities, this is something that's very important, that you can get the current status of well, the whole information, which lanes are currently green, which lanes are currently red, where you can go, where you can't go. All this information would be encoded in this kind of message. Okay, this was a kind of deep dive, but yeah, to get a little bit of information how this could look like. So how do we transport this to a vehicle then? How does the vehicle know that this message is relevant? So let's take the example of a denim message, roadworks warning. This consists of a position and some path leading to this position, right? And the path leading to this is what is encoded in the message. And when a vehicle receives this kind of message, then it also checks if the path that it goes itself, if this path is aligned with the trajectory leading up to this position. If it is, then it concludes that the message is relevant and will will react accordingly. If it receives the message, but this is somehow not aligned, then it concludes, okay, well, this is not relevant for me, right? And it would, for example, not show the message to the driver, something like this. Let's have a look again at this video. I've shown this before in the keynote speech, but now there is something here on the right-hand side. This wasn't there before. I don't know. So if you noticed, here is the visualization of our analysis tool, and you can see here what happens actually on the CITS side when this message is received in the VW. I will, yeah, just have a look here. So here is the roadworks trailer, and it sends out a CITS message. This is the message here with with those points, and this is the trace leading up to the event position actually. And this is what the vehicle recognizes. It is here already on this path, and defined by VW, defined at a defined point distance to the event, it will show to the driver that it is relevant. I think this is more or less clear when seeing this here. Okay, and then there is some other important point, because I'm always saying, okay, so we in ASFINAG, we are rolling out this Wi-Fi standard. It's called ITSG5. It's actually, the frequency is a bit higher than your router that you have at home, but it's not mobile internet, as you've seen just now. It's something else, but it's not the only way how you can communicate this to the vehicles. Of course, you can communicate it too via the mobile network, and this is definitely some other way that should be used, that ASFINAG is providing all the data to, up to basically here, where everybody could in DATEX2 format for the experts, so everybody could take it and distribute it via cellular network too. The thing why we decided to roll out this one is, well, first of all, this is market ready, and this is not so market ready. For example, also an Infomix project, if you're familiar with this one, showed that. And the second one, as I just said, this is really the direct path. So we definitely think that this is something that's great too, but not for time critical things. For time critical things, I would definitely rely on this one, because it's the direct one, currently at least. Okay, what's next? This is what I've already shown you also the slide in the last presentation, but let's talk about it once more, a bit more in detail. So also these kinds of things is something that you can encode into a CITS message. This would be the so-called collective perception message. Something that we did not have on this slide with the 4 messages before, but you can encode objects and well, their position and their heading and something like this, basically an object list into a message, and broaden the electronic horizon of a vehicle via this bird view that I've shown at the beginning of my keynote speech. And for example, that you can send out a message with all the information of the vehicles here, and this then holds more information that the vehicle sees itself. And also, if you detect maybe a broken down vehicle, then, well, you can send out even maybe a warning message, which would be a denim then again, right? And yeah, all kinds of services. For example, I highlighted the platooning service, what we've seen here, the collective perception message, and the GNSS correction data for Esrium, something that we would like to look into in the Esrium project. In, for example, this use case 3, where we would like to have a look if it's beneficiary to have this correction data also via CITS. I think you might be familiar with the correction data via mobile network, but would be interesting to see if it's beneficiary and how it's beneficiary to also get this via CITS. And well, something else that we've seen already in some other presentations, of course, all those kinds of messages, they would be disseminated also via CITS, even though this is something that's more targeted really to automated vehicles, because, for example, there is no real road sign for a vehicle that could tell you, okay, please drive maybe 20 centimeters more to the right, that you are used to be. First of all, this is difficult for a human driver, and secondly, yeah, so this is just something that's really targeted to an automated driver, so it wouldn't be shown there just to, but it would be sent out via CITS and as targeting to an automated vehicle. Yeah, this is about it. I think there was a poll ongoing too, at least I hope so, on the side. And yeah.
So the first poll was open. I can start the second now.
Ah, okay.
Because you said you want the second one at the end of the presentation.
Right. You're right. You're
so
right.
This is open now.
Okay.
Okay. Yannick, thank you for this second presentation and a more detailed insight into the use cases of CITS. If there are questions in the chat, if not, feel free to ask. One question from my side. So earlier you mentioned CITS, of course, creates a benefit even if it's not deployed on the whole highway network of Austria.
Yep.
Still, what percentage of deployment do you envision, like in the next few years?
Well, it depends on what you're looking like. So we percentage. So basically, you have to give me 3 minutes on that. Sorry. So it's first of all, you have to understand that with those roadside units, you don't really need to have full coverage to cover actually what you want to transport to the vehicles, because you can send out, of course, and this is what will happen all the time. You send out some information that is relevant some kilometers in down the road, basically, right? But you receive it already beforehand, and the vehicle has it on board, and it knows, okay, I have to pay attention in maybe 2-3 kilometers. Yeah. So this is why you don't need really full coverage, because it would be a waste. Rather you need a coverage there where it's important. This is what we do, and there we are planning on covering, well, basically the whole network, but we are starting with currently with the A1 Westautobahn, so between Wien and Salzburg, but I think the next one is then A10, so Salzburg downwards to the south to Carinthia. So this would be the main corridors where it's now really deployed, but also all the main border crossings, because again, if you receive the important message at the border crossing, then you have it on board and the vehicle knows about it when you reach the relevant section, the relevant point. Do you know where I'm aiming at?
Yeah.
Okay.
So it's more or less, say, also like a pop-up network. Like if you have those mobile traffic signs of yours and you have them placed somewhere, of course they're communicating there, but they're not static.
Yeah.
So you cannot really talk about the static coverage of the whole network, but and more of an on-demand deployment on several occasions also.
You could put it that way. However, we are deploying, of course, on corridors. So it's
okay.
Corridor wise. Yeah.
So thank you again, Yannick. And thereby now, having learned about the data available and how to communicate it, our closing session deals with the aspect of how to use such information actually in the vehicle. This part here is covered by the Virtual Vehicle Research Center, represented by Selim Solmaz and Martin Rudiger. And I will gladly hand over now the presentation to you.
Thank you very much, Matthias, for the nice introduction. So let me switch on my screen. Could you please confirm that you can see it?
It works. Thank you.
Yes. Perfect. So before we start the last technical presentation of the workshop, actually, let me briefly introduce myself. I am Selim Solmaz. I'm a lead researcher at Virtual Vehicle Research Center within the group of control systems, and we are working on problems related to and motivated from automated driving together with my colleagues. And I will also let my colleague Martin Rudiger introduce himself before the talk starts. So, Martin.
Hello, my name is Martin Rudiger. I'm working at the Virtual Vehicle and the Control Systems groups in the same group as Selim. And I work on automated driving.
Okay, thank you, Martin. So let me move on to the next slide. So this presentation is about infrastructure-assisted driving functions. So basically, many of the components that we are utilizing in this presentation have been presented by bits and pieces by other colleagues so far, and we will try to put these in context in this last talk. So here the aim is to demonstrate automated driving with infrastructure assistance messages, and with the specific example of routing recommendations which correspond to the use case, Esrium use case 2, if you remember. So this means that routing recommendations with specific information on positioning within and between the lanes based on the road map, and the vehicle will, for example, get the information about a hazard on the driven lane, and then conduct let's say recommended lane change maneuver to avoid the problem location, or as expected by the increase of the penetration rate of automated vehicles, particularly in the form of heavy vehicle transport, automated heavy vehicle transport, or platoons, can induce actually road damage in the form of ruts or surface depressions on while driving on the same lane at the same location, because with automated driving, so if you consider the lane keeping assistance systems, they try to basically keep the vehicle at the center of the lane, and they do this more efficiently or more effectively than human drivers. So the expectation or conjecture is that such vehicle traffic can induce excessive rutting. So in order to prevent this, we have thought about specific scenarios and use cases as a basis for development of our driving functions. So this is based on the road beer map, which was introduced by Johanneum, and CITS messages, which collect this information and distribute to the connected vehicles, let's say, and then the vehicle equipped with a precise localization system can take this into account in the form of new driving functions. Before we proceed further, I would like to ask Martina to place our first poll question. I think this was mistakenly put online during the Johanneum presentation on sensors, so could you please switch on the poll question about the prior knowledge of the audience related to ADAS functions?
I opened it again.
Okay, thank you very much.
So it's available now.
Okay, thank you very much. So if you haven't responded earlier, please do so now so that we have an idea about what is the prior knowledge of the audience on such systems. So moving on to the next slide. So let me now introduce the specific scenarios that we considered in developing our driving functions. You use the, you already know the use case about routing recommendations. Here is the example of the first scenario. Here we have in lane offset recommendations where the vehicle is driving on a specific lane of the motorway and it goes through a detection zone. This is the zone where the vehicle needs to receive the information about the in-lane offset recommendation together with the information of the relevance zone, which means the location where it applies to. So when the vehicle comes to the relevance zone, it conducts a shift maneuver to the side of the lane so that it drives along the relevance zone at this offset. So this is basically what we call as the in-lane offset recommendation. In the next scenario, we have lane change recommendations, and this was already demonstrated very nicely by the let's say illustration from ASFINAG, where there may be a road blockage or road damage or construction zone or some object lying on the lane, which can be used as a basis to direct the connected vehicle traffic to a specific lane or number of lanes. So here you see the example of this use case where the vehicle going into detection zone conducts a lane change maneuver to the recommended lane or one of the recommended lanes and drives through the second relevance zone at this lane, and at the end of this relevance zone 2, it can keep on the existing lane or return to the original driven lane. So this is the use case scenario 2. And our third use case scenario is eGNSS-based local lane recommendation. So this is a bit of more in the future, but in the case that we are able to provide individual trajectories to the connected and automated vehicles, this represents how this can be utilized, where the information in this case will be transferred in the form of georeferenced trajectory and velocity provision information, and this will be then extracted and parsed to generate reference path and velocity information for the driving functions such as ACC, LK, as well as trajectory planner, and this will be then used as a reference for the vehicle to follow. We will actually demonstrate all these use cases, especially the first two on the motorway in real public roads, which is actually already designated as the A2 motorway near Graz, Austria. But this one will be only tested on enclosed proving grounds. Okay, so let me also briefly mention about our development framework or environment. So we did we performed our development in simulation. in a simulation framework. It's a co-simulation framework composed of a vehicle dynamics simulator based on RPG KineMaker and MATLAB Simulink environment for developing the driving functions. We prefer this platform to do the development because our test vehicle, which we want to use later on in the project for real road demonstrations, can exactly use the driving functions that we develop in MATLAB and run it on the real-time ECU, which is based on D-space micro-autobox on the real vehicle. So in the real test, the vehicle dynamics simulator will be replaced by the car itself, and the driving functions will be the same driving functions that we use in MATLAB and running on the D-space micro-autobox on the vehicle. So here we also have Ultra HD maps, which are HD maps that we utilize in the form of Road 5 format for scenario setup within the IPG CarMaker software. And then we have the communication component. Actually, in driving function development, we have not modeled the communication, but rather we use the parsed information or the recommendation itself as a trigger message, and then use this as an input to driver functions. And we can actually realize this, let's say, scenario in one way. As you can see on the right-hand side, we will see further visualizations later, but here you can see what goes into the vehicle driving function in the form of lanes and a reference trajectory follow, where here the reference trajectory is shifted to the right for an example. And with that, I would like to pass the floor to my colleague Martin for description of the driving function.
Okay, for this use cases, we use a rule-based trajectory planner. It has a set of discrete decisions to trigger lane changes or keep that vehicle on the current lane. It is suitable for structured environment like highways, not for towns or road in country roads. The default behavior is keep the vehicle in the middle of in the rightmost lane, and only if there is a IV message or a slower vehicle, the driving functions triggers a lane change to another lane. The lane change is done with two quadratic Bézier curves and a connecting straight.
Next slide.
Next slide, please. For these use cases, we have to add additional functions. We need a emulation of the passing and of the receiving and passing of the IV message for both scenarios. For the inline offset recommendation, we need a direction zone, a relevance zone, the offset, and the lane which is the offset dedicated to. And for the second scenario, for the lane change recommendation, we need one direction zone and 3 relevance zones. Next slide, please. We have first results of simulations on a straight road section without traffic, but we are working on the simulation on the A2 at the moment, but we have no slides from this at the moment ready. This is the result from the inline offset recommendation. In the upper figure, you see the steering wheel angle. In the lower figure, you see the Y offset of the vehicle. The vehicle is driving along the X-axis of the road, and the Y offset is the offset to the center line. At the beginning, we start with 0 offset, and in the detection zone, as the DZ, we get an IVIM with the message to drive with an offset. The vehicle is shifted to the offset, the demanded offset, and in the relevant zone, the vehicle drives with the offset, and after the relevant zone, it is shifted back to 0 offset. Next slide, please. This is a simulation result of the lane change recommendation. Again, in the upper figure, you see the steering wheel angle, and in the lower figure, in red, the desired lane path. The lane 0 is the right lane, and lane 1 is the left lane. We start on the right lane. In the detection zone, we receive the message. And in the relevant zone 1, we search for a gap on the traffic situation. If it's possible, we change the lane to the left lane. And in the relevant zone 2, we avoid the damage by driving on lane 1. And in relevant zone 3, we change the lane back to the right lane. Next slide. This is a combined scenario. We see several runs with different inline offsets. The vehicle starts at 0 offsets, goes to the demanded offset, then lane changes the lane due to a slower vehicle in front, and drives without offset on the right lane and the left lane. And then after overtaking, it changes back to the right lane and drives with the same lane of inline offset as before. Next slide. Now we see a short video of this use case. The vehicle drives in the middle of the lane, and now it is shifted to the offset, demanded offset, 40 centimeters on the right, and is approaching a vehicle in front of him and makes an overtake maneuver. Then it drives back to the right lane and drives again with minus 40 centimeter offset until the relevant zone ends. And then now it's shifted back to 0 offset. Next slide, thank you.
Okay, so thank you very much, Martin. So now let me give a future outlook on this work. We have just very recently published the initial implementation results in the simulation in an MDPI electronics journal, which is publicly available as open access on the electronics website, as well as on the Esrium website. So if you're interested, you're more than welcome to visit our project website to have a look at this paper. We are at the moment in preparation of a second paper on the KPI analysis of the driving functions for the IEEE ICCV. So conference, this is the International Conference on Connected Vehicles and Exposition, which will take place in Florida, USA in early 2022, I think March. In a hybrid form. So we hope to present our additional results here. So what is the next steps in this development work is the implementation of the algorithms on the real vehicle itself. And for this, we have to first clear a pair of hurdles. The first is the integration of an EGNSS localization system in our car, as well as an ITSG FAF OBU onboard unit, basically, so that we are able to localize ourselves and actually communicate with the infrastructure available that we have in ASFINAG operated motorway here. So, and then we are planning to conduct our first localization test together with ASFINAG, utilizing the RTCM correction messages, and then actually evaluate the localization performance. And then as a next step, we are planning to test our hardware implementation first in the enclosed test tracks of what is similar to what we have demonstrated already in simulation, and then later on the public motorway. So with that, we have come to the end of this presentation. And before we close the presentation, I would like to ask Martina to place the second poll, which aims to get your feedback on what you have seen in this presentation.
It is open.
Okay, perfect. Thank you very much. So thank you very much. And we are more than happy to answer any questions if there's.
Thank you, Selim and Martin, for this presentation on how to actually exploit driving recommendations and other information right in the vehicle, and how this can contribute to the future of vehicle automation. I'm having a look at the chat if there are questions. I don't see any questions right now. So let me put a question to you. Considering the levels of automation we have seen before, what do you see is the lowest level of vehicle automation where actually such information can be of use to the driver and the vehicle?
Yeah, personally, I think that the minimum required level is level 3, because at level 3, this is the conditional automation, and in well-defined ODDs, the vehicle can actually take decisions itself, and the driver is not responsible of liable of driving safety. And in this case, I think the application that we have presented or suggested corresponds to partial liability. So I think it would require at least level 3. Martin, would you have additional ideas on this?
Oh,
okay.
There has been an additional question in the chat. So currently, at the time being, and in our use cases, we have been talking about high-level roads, especially highways. So what do you think are results of Esrium transferable to urban or suburban areas, especially what driving functions are concerned?
Yes, I think they can be also transferred on urban and suburban areas, as far as there's infrastructure to support this. Yes.
Thank you for that.
Welcome.
If there are no further questions, it is up to me now to sort of round up our today's workshop and now get an insight also, or provide an insight of what the results of our polls have been in the end. So in my opinion, regarding the scope of the whole conference, which puts the frame on our workshop today, which is computer vision systems, I think our highly mobile computer vision solutions we have within this project, and also within mobile data capture and analysis, they are a bit different than what one usually has as computer vision system, because we have a single producer, multi-user environment. We always need to scale to, like, all traffic, all users of traffic. We need to consider several levels of automation there, and thereby always need to take into account a more scalable solution finally, which somehow puts also a special requirements and a special case in terms of how to design such systems there. But let me now switch to the results of our polls. I think the last one, I can also close the last one right now and see to the analytics. So,
Matthias, can you please make it full screen?
yeah, I'm just having a look if this have been all questions. I don't think so. So this was the first one.
So we voted 8 polls, I think.
We voted 8 polls, right? So I'm doing it like that. And this one I can now do like full screen. And if I start it right now, yeah, now we see there's the results. Again, so our first question was, how do you rate the importance of GNSS-based use cases, like we do in Esrium, for the predictive road maintenance? The poll is open again, so there might be slight shifts here. Yeah, so there is a ramp towards really high importance. So 5 was highly important, I guess. Here, I would also now like to get the opinion of the presenters, how you see this result. Any comments?
Yes, so as far as I can see here, yes, I think it's the participants' view that it is highly important. A lot of votes there for the sections 4 and 5 there. So yes, yeah, that's one of the main results that we can take with us for the next course of the project.
So then I'll jump to the next one. How would you rate the acceptance rates or compliance of truck drivers to CITS messages like recommended lane provided by a road operator? So here the expectation is that acceptance will be not quite high. Here it's certainly something to consider. What's our opinion from the use case side here?
Yes, that is to be honest, the answer that we have kind of expected here as well, because taking the point of view of a truck driver, changing the lane due to smaller incidents might be considered inconvenient for the driver himself. So that's why we have formulated the following question as well for what incentives could be given to truck drivers in order to achieve a higher, let's say, a higher compliance with the routing, the lane change service. So that's one of the results that we have expected here.
Okay, so also the view on it would be that it's perhaps, or a takeaway message would be that one might need strong incentives actually to have someone who really does his job on the road, and where his own money depends on like efficient driving on the road, that he also needs incentives to like assist a road operator finally.
Exactly, yeah.
Yeah, this is now also reflected probably in this message here. How would you rate the importance of benefits, for example, reducing tolling for truck drivers' acceptance of such messages, which is deemed quite high here? So probably this goes in the same direction. We need somewhat an incentive, and if the road operator sort of has a benefit from it, the question is what benefit comes to the truck operator actually. One interesting question to the audience: what is your knowledge level of automated driving technologies and ADAS systems? So regarding that, our answers have been knowing what they are, but not really a technical background. So we have two extreme cases actually now here. So half of the audience actually is in the field, and the other half says, okay, basic knowledge. Experience of driving such vehicles, along with a good understanding of how they work, is a twofold question. So one sees that it's actually quite low. If we now consider this would be like from level 3, meant from level 3 or above. This somewhat also might reflect the market penetration of such systems already, but which is also interesting, at least for the participants of this work package, there is no one who has totally no prior knowledge of it. So this might also reflect the general knowledge. We now have a more technical audience here, of course, but it might also reflect the general knowledge and public attention coming to this field in an increasing manner. Any opinions on that from your side?
Yes, Matthias, I think this is also quite interesting for the last poll, at least from our side, because to predict the meaning of the acceptance rate of the suggested driving functions, I think this is a very good input. So.
Okay, very good. Next questions. Do you believe that the utilization of the suggested automated driving functions can improve road safety? Consider that such automated vehicles will have to coexist with conventional and manually driven vehicles for the foreseeable future. Here we get quite a clear yes, I would say.
Yes, I agree, and I think this is quite positive by the people who are in this field. I think this is perceived as very positive, which is quite supporting for us. Of course, it's interesting how would the people who have no prior experience or knowledge about such systems think about these innovations, which is not really addressed here, but I think the result is overall very interesting for me. Yeah.
Thank you. Okay, there are several polls now we actually didn't put online, I guess, which are very specific if you would be willing to pay for certain. This one is quite interesting also. going into the direction of car-to-X communication, which might be not so much of a popular topic in comparison to the general aspect of automated mobility. So the question was, had you heard about CITS before this presentation? And here, this is rather twofold. So there is yes and no, and I've heard about car-to-X CITS, but not in detail. So there might be a majority, a slight majority, which is not that highly informed about it.
Yeah, interesting to me too, because know your audience, right? So I hope for a third of the people it was completely new, and I hope that it was the right level of detail then for those people. Yeah. But I was aiming at the third actually that has not yet heard about CITS before with my presentation. So that's good to know. Yeah.
Mm-hmm. So perhaps to put it in another way, is it necessary to have like a broad audience informed about such a technology, or will it evolve sort of anyway to something transparent to the general audience, and it will become sort of another warning light in the car? So Yannick, what do you think? Do people really have to know about this technology?
Well, currently, since it's not so popular now, it's of course a good idea to make it a bit more popular if you are working in this kind of field. However, as you said, if it really takes on some pace or something like this, then I think people will know it if it's a kind of system that's in the car. Even though it might be, I have to admit, it might be that people don't really know where the information comes from, on the other hand, right? So people don't really care if the information that is displayed in the car is coming via some direct link or via some backend or something like this. So yeah, also not 100% sure, to be honest.
All right, thank you. When do you think you will be using CITS on a daily basis? Here the time range is in tendency is quite short. Yannick, do you think this is in line with, say, the technical evolvement in this field?
I think so. Yeah. The thing is, of course, it depends a bit on the car manufacturers too. But basically, the first cars using this technology are already on the market, and then if it really, if it really gets momentum, maybe, let's put it this way, then this question is more or less, when will you buy your new car? You know, if it's something that's gonna be standard equipment, depends. Yeah.
Okay, thank you. Do you think the road wear map data layer could help to improve road safety? Okay, there have been several options. It helps road operators to better organize road maintenance, or it helps vehicles to avoid potentially dangerous road sections. There, the the majority said both answers are relevant, so which also reflects our use cases actually have relevance. What is your opinion? Additional comments to that? Well, if not, Martina, I think this have been all polls we have been addressing, right?
Yes, this is the last one. This was from Andras. I don't know if he wants to comment on it, but nothing was missed.
Okay. So thank you. So then from my side to there has been a suggestion also from Anarita, because we missed some of the polls here also for time reasons, that we add another one. Just let me check. Which one?
So actually, the question is always the same. It's just for the 4 different use cases.
Yes, so I would suggest considering all use cases, or the major use cases for the end user we have heard. Would you be willing to like pay for such a service? So the first one was now AI-based road damage prediction to support planning. I can see there are votes.
Yes, I have a question here. I mean, what does you mean? Is it infrastructure operator, or is it end users, drivers?
Yeah, so actually, two things are hidden in the question. First of all, the data needs to be relevant for you, of course. So it doesn't address the end user, but more the road operator. And then the question is, would you be willing to pay for it? So I'm a bit in doubt if we get good volume feedback here. But let's see how this works out. So here we get now like the answer more no, which might also mean that the data simply is not relevant for one as a, say, driver on the road, which is also clear. Okay, so the majority is rather a no. Let's jump to the next one. Routing recommendations within and between lanes. This is clearly something which, say, everyone would be concerned with if he or she owns a car equipped with this equipment. So here the question is, would you, despite the benefits, would you be willing to pay extra for such a service? I think the development is quite clear here. Okay. So an extra payment from the road user who probably already pays tolls to some extent in most European countries would not really favor an extra payment. So this is, I think, the second last question on this. So for each GNSS correction data, which ultimately allows a car to be precisely located on the road, would you be willing to pay for this service? Here, probably the question also is who is addressed, because ultimately it goes to implementers of services based on such a correction data in the end. So, and here also the question is a majority also in the no direction. So I'll set up the last questions, which would be like where map content provision, which is also more addressed to like the road operators, I would say.
No, actually not. Sorry to correct you, but it's no, it's this. This is the use case that's actually really to the end user. So this.
Okay, so that you really get the road, the content information.
Because
in the
this
okay.
There is no road operator involved in this one. Yeah.
Matthias, I think this is more in the direction of service provider or OEM. So,
or navigational provider or somebody.
Yes, service provider meant that.
Yeah.
Right. So I think that if we are now to summarize the answers we had before, of course, for a complete questionnaire, one would now need the type of audience who answered specifically, but I think there is a general tendency from an end user side that there is a majority voting for no extra payments. But this somehow also reflects the type of technology we have here, which would be sort of a back-end technology, which would have to be put into specific end user oriented services finally, and probably also support, in some cases also supported by incentives if it comes to road wear optimization. All right. Additional comments from your side on those results?
So actually, it would be nice to have answers to these questions from a broader audience.
Sure.
So I'm not that sure how representative these results are at the moment, because there are not that many votes and most of us are from within the project. So we should consider getting additional feedback from the outside.
Of course, yes. So in this course, to round up today's workshop, I think it was quite productive, and I think it was our first real public representation of the whole project in one event. So from my side, it went quite well, and I thought we also gave a good overview. I hope that we have the contact list in the end, that we also send out a final feedback poll to the non-project audience, so we get feedback on how they received this whole workshop and what they made of it. So from my side, I would now be interested in a short feedback from your side, what your opinion on this workshop is, what our next step should be in terms of dissemination, and yeah. What we could do in this respect.
Matthias, I would like to also support Martina's idea that maybe to have more meaning to these polls, I think we need to reach a bigger audience. But otherwise, I really find the workshop format and the presented results quite interesting. So from my side.
So thank you for that. And yeah, since we are right at the end of our time frame, then I would like to thank all the participants, all the speakers for the preparation of this workshop, and let's take this drive, also the presentations, and continue our dissemination efforts also on the project. And also based on this, I think we have a good basis now to really also link up with other EU projects and do a bilateral exchange also for them. So thank you from my side for today, and I hereby would like to close our today's workshop and the final session. I wish you all a good weekend and a productive follow-up work in the project Esrium or in mobile infrastructure mapping as a whole. Thank you.
Thank you very much.
Thank you.
Thank you very much.
Thanks. Bye.
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 Thank you. See you later.